Welcome to Lecture 9. As a result of a question that one student raised during our last test, I realized that there's been one issue I've overlooked that I'd like to clear up at the present time. Suppose that we have the following. F of xyz is equal to let's say maybe x prime y z or x y prime z prime. Now this is called obviously, first of all, this is a minterm expansion because this is both of these are minterms. They are simple products of all of the available Boolean variables in either complemented or uncomplemented form, and we have a sum of these products. So this is a minterm expansion of f. A minterm expansion of f. In fact, I'll say the minterm expansion of f because it is unique. The minterm expansion of f in algebraic notation. And by algebraic notation, we mean that where the variables are all spelled out. Now, as we learned before, we can also have f of xyz in what's called decimal notation. And the way that we get that is as follows. For each one of these minterms, we look at what the variables need to be in order for each minterm to be equal to 1. Remember, for minterms, we look when they're equal to 1. For max terms, we'll look at when they're equal to 0. So for this first minterm to be equal to 1, we would need x is 0, y is 1, and z is 1. And for the next term, actually, I want to make a small change in that next term. I'm going to make that x, y, z prime. Don't worry about my reason for that. It just I'd prefer to have that. So to make this minterm equal to 1, we would need 1, 1, 0. Actually, now that I think about it, well, okay, let's just, okay, yeah, let's leave it at this. Okay, so we have x prime yz or x y z prime. This is the minterm expansion of f in algebraic notation, and now if we wanted the minterm expansion of f in decimal notation, the way that we get that is we identify when each minterm is equal to 1, and now we interpret these as binary numbers. So the binary number 0, 1, 1, when written in decimal, would be 3, and the binary number 1, 1, 0, when written in decimal, would be 4, and 2, and 0 is 6. And so in decimal notation, we would have this. And this is the minterm expansion of f in decimal notation. Now, the point, another point that I wanted to make, besides introducing this terminology of algebraic notation and decimal notation, the other point I wanted to make is the following. If we wrote f of xyz is equal to y x prime z or y z prime x, notice that that is still a minterm expansion for f, but the two minterms are written in an order that does not match the order of the variables given in the argument of the function. And if you don't notice this, if you just begin the numbering, well, this would be 1, 0, 1, and this one would be actually also 1, 0, 1. And you might, who knows, you might even be misled if you saw that the numbers were the same there. You might even be misled into combining those two. Of course, they don't combine at all. But it's let's say that maybe you recognize the error here, and you change this last term to y x z prime, and then you would have 1, 1, 0. Well, even if you did that, though, and now you interpreted these as binary numbers, you would have 5 and 6, when in fact the correct answer for the decimal notation of f is 3 and 6. And the reason that we have been led to the wrong answer here is that in our minterms, we did not list the variables in the correct order. And what is the correct order? Well, it's the order in which the variables are listed in the argument of the function. So whenever you're listing out minterms, or maxterms for that matter, make sure that the variables appear in the same order that they do in the argument of the function, and then you'll be able to do the decimal notation or algebraic notation. You'll know easily what you should use there. So that was just one note that arose at the end of our during our last test, and so I wanted to make sure you were aware of that. So now I'd like to do a problem to give us a little more practice with all of this. If you have the book, again, that's edition, the 6th edition of Roth's book, Fundamentals of Logic Design. This problem is 430, but for those who don't have it, I'll go ahead and spell out the problem. It tells us to find both the minterm expansion and the maxterm expansion, for the following functions. Now, it also specifies using algebraic manipulations, but I'm not going to stipulate that you can only use algebraic manipulations. I'm going to allow you to use anything you wish in order to find the answer. So here we have A. It says lowercase f of A, B, C, D is equal to AB, or A prime C D. And we first will find the minterm expansion, and then we'll find the maxterm expansion for this function. Now, to find the minterm expansion, we first want to observe that neither one of the terms here is a minterm. The first term is not a minterm because it doesn't have either C or D in it, and the second term is not a minterm because it doesn't have B in it. And we know how to correct these deficiencies. For the first term, we will AND it with 1 twice. We'll write the first one as C or C prime, and the second one as D or D prime. And for the second term, we will AND it with 1 one time, and 1 will be written as B or B prime, since B is the missing variable in the second term. Now we multiply this all out, and do be careful. I noticed with some students that when they had two parenthetical expressions like this to multiply with each other, sometimes they would only multiply the outside terms and forget the inside terms. So in other words, what I mean is they would see CD and C prime D prime here, but they would forget CD prime or C prime D. So be careful when you're multiplying terms together to get all of the terms. So we will get AB, and we'll have CD or CD prime or C prime D or C prime D prime. And the second term only has one parenthetical expression, so it's a little bit easier. We'll get A prime B C D or A prime B prime C D. By the way, I forgot when I started this problem, but to be honest, I think you can probably do this problem on your own. So if you haven't already done so, I would encourage you to stop the video at this point and try to do this problem, try to finish this problem on your own, and then come back. Okay, so let's now finish this problem. When we multiply out this first term, we'll have AB CD or AB C D prime or AB C prime D or AB C prime D prime, and then we bring down the terms from before. For the second term, A prime B C D or A prime B prime C D. Now, everything we've been using here, you remember I mentioned that the book specified that you wanted to find the minterm and max term expansions using algebraic manipulations, and everything I've done so far here in trying to find the minterm expansion is an algebraic manipulation. And in fact, we will only use algebraic manipulations in finding the minterm expansion. But then to find the max term expansion, rather than starting back here at this original expression and using algebra, we'll use a faster way, which we've already talked about. But we'll get to that in just a moment. Anyway, now we're ready. We can agree, I think, that every term here is a minterm. Notice that in each case we have a simple product of all of the variables. The variables are in the right order, and so we can go ahead and the book does not tell us whether we should give the expansions in algebraic notation or in decimal notation, so I will choose to give it in the decimal notation. That's shorter, and also I personally think it makes it a little bit easier to check for redundancy. And so let's go ahead and find out how this would be listed well, actually, I guess I should say the following. So this is the function f of a, b, c, d. And if we check this, we can see that in fact there is no redundancy here. In other words, no term has been repeated. And therefore we're done if we're satisfied with having f in algebraic notation. So I'll go ahead and say, I'll circle this, and this is the minterm expansion. for f of a, b, c, d in algebraic notation. Okay? So that's really all that the problem asks us for. So if you wanted to now, you could go ahead and you could repeat this function f of a, b, c, d equals ab or a prime c, d. You could write it like that and then use algebraic techniques to find the max term expansion. And the way that I would go about doing that, in fact, maybe we should just do that just as a good practice, but then I'll show you a quicker way to do it. So let's find the max term expansion and I'll say 1, use algebraic. Manipulations. Okay, now this is similar to the kind of thing we've done before. Let's go ahead and repeat our function f a, b, c, d is equal to ab or a prime c, d. And now if I wanted to use algebraic manipulations to find the max term expansion, my approach would be as follows. I noticed that this is a sum of products, or SOP expression, and of course I know that the max term expansion is a POS expression. And we learned, we've already seen a couple of examples in which we saw that one convenient way to get from an SOP expression to a POS expression is to complement twice. Because remember, anything complemented twice is itself. Like x prime prime is x, or y prime prime is y. So double priming anything does not change its value. Now, what we'll do, I'll go ahead and just remind you that the way that we will approach this problem is the following. We will treat those two primes separately, and so for the inner prime right here, this is the complement of a sum, and by one of De Morgan's laws, the complement of a sum is the product of the individual complements. So we have AB, that's one term, and we want its complement, and the other term is A prime CD, and we will also want its complement. So again, we're saying that the complement here, the complement of a sum, is the product. You can see that this is a product here. If you want, you can put a little dot just to emphasize that this is a product. This is a product of the individual complements, and then we don't want to forget the prime on the outside. Now, on the inside, since each of those terms is complemented, we can use De Morgan's theorem again, and this time, since each of those is a product, we will be using De Morgan's law for the complement of a product, and that one says that the complement of a product is the sum of the individual complements. So we have A prime or B prime for the first term, and then for the second term we'll have A prime prime, which is A, or C prime or D prime. And once again, we have just twice used the De Morgan's law that says the complement, here the complement of a product is the sum of the individual complements. Okay. Now what we do, we're almost done with this, but now we will go ahead and multiply out what's on the inside of the brackets. A prime A, I hope you readily see that that's equal to 0, because remember, any variable ended with its complement is 0. So A prime A gives nothing. Then we have A prime C prime, or A prime D prime, or A B prime, or B prime C prime, or B prime D prime. And all of that is primed. And now we will finally get a POS form by using De Morgan's law for this, which says the complement of a sum is the product of the individual complements. And so we have A prime C prime prime ANDed with A prime D prime prime ANDed with A B prime prime ANDed with B prime C prime prime ANDed with B prime D prime prime. Again, this complement here on the outside, the complement of a sum is the product of the individual complements. And so you can see what we have there. And now if we use De Morgan's laws for each one of those is the complement of a product, and we know the complement of a product is the sum of the individual complements. So we have A or C ANDed with A or D, ANDed with A prime or B, ANDed with B or C, and finally ANDed with B or D. And notice in each case we've said the complement of a product is the sum of the individual complements. So that's why A prime became A, C prime became C, A prime is A, D prime is D, A becomes A prime, B prime becomes B, B prime becomes B, C prime becomes C, B prime becomes B, D prime becomes D. And notice that now we have indeed achieved a product of sums expression. However, our goal was to get a max term expansion, which is a special kind of POS expression. And you can clearly see that this is not a max term expression, because in fact not a single one of these terms is a max term. Remember that to get a max term we need to have all of the variables present in either complemented or uncomplemented form. So the question becomes now, what do we do to move from this POS expression to a max term expansion? And I will remind you, recall that X or Y ANDed with X or Y prime, that is equal to X. And I think you can see that that's true, because X ANDed with X would be X, x ended with y prime would be absorbed into x ended with y would be absorbed into x, and y ended with y prime is 0. So we will now, for each one of these terms, we can use that notion going backwards. So A or C is the same thing as A or B or C ended with A or B prime or C. Now, let me make sure you follow that. I'm thinking here of A or C as being like X, and then I'm thinking of B as being Y. So here you can see A or C or B, that's X or Y here, and A or B prime or C is the same as the A or C part is, again, that's X, and now B prime is Y prime. So I have things in a slightly different order, but we're thinking of A or C, that's playing the role of X, and B is playing the role of Y. And we're going not from left to right in this equation, but from right to left. So we have this one term A or C, think of that as being X, and we're going to the left, from right to left, we're rewriting it as X or Y ended with X or Y prime. So we have two terms, we have one term here that becomes two terms down here. And we'll do the same kind of thing with each of those terms. So the next one can become A or B or D ended with A or B prime or D. The next one can become A prime or B or C ended with A prime or B or C prime. And the next one can become A or B or C ended with A prime or B or C. And finally, the last one I'll write as A or B or D ended with A prime or B or D. Now I want to emphasize that we still don't have max terms. We have 4 variables in this problem. F is a function of A, B, C, and D, as we can see right up here. And our problem right here with our POS expression is that we have a product of sums like we want, but those sums, each one of those sums is a sum of only 2 Boolean variables, and we need each one to be a sum of 4 Boolean variables. So we're going to need to use this property repeatedly, this X or Y ended with X or Y prime equals X. We're going to need to use that over and over. But to be real careful, I'm just doing it once, one at a time. And so, like for instance, what I mean there is that we need both B and D in this first term. You see we have A or C. We're missing B and we're also missing D. But I'm not going to try to introduce both at the same time. I'll just introduce one extra variable at a time. And so for the first one, we have B prime. For this next one, we have B prime. The next one, notice that C and D are both missing, but I'll just first introduce C. So that's why we'll have A prime or B or C, and with A prime or B or C prime. And then for this one, I have A and A prime, and for this one also A and A prime. And then my goal next, in the next step, would be to introduce in each case, the one more missing Boolean variable. But before we do that, we do fortunately have some simplification. Notice that right here we have A or B or C, and notice, recall that we have an and here. So we're continuing this on the second line, but in the second line, one of the terms we see is A or B or C. And anything ended with itself is itself, so we don't have to repeat A or B or C, and we can cross out one instance of that. Likewise here, the third term is A or B or D, and so is the next to last term, A or B or D. So I can cross out one instance of that. And the term right here, the next to last term in the first line is A prime or B or C. And that matches this term down here, the second term in the second line, A prime or B or C. So I can get rid of that term. And let's see, I don't believe that there's any more repetition, so I'll leave it at that. And now finish this up. Now you can see this is quite tedious, and keep in mind just how tedious this is, because you're going to see that there is a much easier way to do this, which we'll discuss in just a moment. But first, let's finish this up. Now, we still have a POS expression here. This is a POS expression. And it is closer to being a max term expansion than was our previous POS expression, but it's still not a max term expansion, and I hope you readily see that that's the case, because each one is still missing one variable. And so again, we will use this very handy fact that we have here. So A or B or C will become A or B or C or D, ended with A or B or C or D prime. And A or B prime or C will become A or B prime or C or D, ended with A or B prime or C or D prime. A or B or D will become A or B or C or D, ended with A or B or C prime or D. The A or B prime or D will become A or B prime or C or D, ended with A or B prime or C prime or D. And then A prime or B or C will become A prime or B or C or D, ended with A prime or B or C or D prime. And finally, the A prime or B or C prime term will become A prime or B or C prime or D, ended with A prime or B or C prime or D prime. And now we begin, now we notice that this is still, of course, a POS or product of sums expression. Each one of these terms is now indeed a max term, but we need to remove redundancies, and we can see there definitely are some. In fact, remember now, I want to emphasize that all of this is just one big product. It's the product of 12 terms, but there are quite a few redundancies. In fact, we see A or B or C or D is repeated here, and so we can take out one instance of that. And let's see. A, here we see A or B prime or C or D, and A or B prime or C or D, so we can take out one instance of that. And it's hard sometimes, at least for me, it's hard to see these redundancies. As I say, I like to go to the decimal notation, for me it's easier to see if there are redundancies in that way. Maybe some of you see some other repetitions, but I think I'll go, before I'm going to say that this is the max term expansion for f in algebraic notation. Before I'm going to claim that for sure, I want to look at the decimal notation. So let's see what that would be. Now remember, for max terms, the way that we label them is by when they are equal to 0. So the first term, we would need all of the variables to be equal to 0 for the first term to be 0. For the second one, we would have 0, 0, 0, 1. For the third one, we would have 0, 1, 0, 0. And for the next one, 0, 1, 0, 1. The next one, 0, 0, 1, 0. And the next one here, 0, 1, 1, 0. And going to the final line, we have 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, and 1, 0, 1, 1. Now let's look at each of those things that we just wrote and write it. Think of those as being binary numbers and translate them to decimal. So we have, remember that for a product, we don't use, remember for a sum we use this symbol, but for a product we use this symbol right here. It looks almost like the Greek letter pi. And so we have, and remember again, for max terms we will have capital M, and 0, 0, 0, 0 is 0, 0, 0, 0, 1 is 1, 0, 1, 0, 0 is 4, 0, 1, 0, 1 is 5. Going to the next line, 0, 0, 1, 0 is 2, 0, 1, 1, 0 is 6, and now going to the last line, 1, 0, 0, 0 is 8, 1, 0, 0, 1 is 9, 1, 0, 1, 0 is 10, and finally 1, 0, 1, 1 is 11. And we can see there now we do need to write these numbers in ascending order, which means we need to write the 2 over here after 1, but we can readily see that there is no redundancy, and therefore we can go ahead and write f of A, B, C, D, and likewise f of A, B, C, D here, and we can conclude sorry about that. Okay, we can conclude that these are max term expansions for f. This is this first one is max term expansion in algebraic notation, and that's this, and this, well, let's go ahead. Actually, we probably ought to make this a little neater, get rid of all the numbers, and also get rid of the redundant terms. So maybe I should just repeat this. So let's maybe cross that out, and we'll just say f of a, b, c, d is equal to a or b or c or d ended with a or b or c or d prime ended with a or b prime or c or d ended with a or b prime or c or d prime ended with a or b or c prime or d. Notice I'm taking out the redundant terms from above. Ended with a or b prime or c prime or d. Ended with a prime or b or c or d. Ended with a prime or b or c or d prime. Ended with a prime or b or c prime or d. Ended with a prime or b or c prime or d prime. That we've already verified now that has no redundancy. Each term there is a max term, so this is the max term expansion for f of a, b, c, d in algebraic notation and f of a, b, c, d is equal to the product of the max terms 0, 1, 2, 4, 5, 6, 8, 9, 10, 11 is the max term expansion for f of A, B, C, D in decimal notation. And if you thought that was painful, it's because it was. That was a tedious procedure. And so now I want to show you a much more efficient procedure for finding the max term expression in cases like this where you already have the minterm expansion. So this will be, I'll say, alternative method. Now let's go up, scroll back through all this work we've just done, and notice, let's just take a look at this minterm expansion that we found before. Now remember, the minterm expansion was very little work, and that's typical, especially when you start off like this. We notice, see, this is already a sum of products expression, and when you start off with the sum of products expression, it is typically quite quick to get the minterm expansion, just as we did here. Now we're charged with finding the max term expansion, and we would like to do this as quickly as possible. Well, let me show you the quickest possible way. So I'm going to repeat the minterm expansion down here. That's A, B, C, D. So we'll say, recall that the minterm expansion is f of A, B, C, D. Actually, I'll just start a new line here. F of A, B, C, D equals A, B, C, D, or A, B, C, D prime. The next two terms are A, B, C, D prime and A, B, C prime D. A, B, C, D prime or A, B, C prime D. Now to scroll back up and find the next two terms. The next two terms have C prime, D prime, and A prime. C, D, and A are the prime terms. So A, B, C, D, A, B, C, D, and we said C prime and D prime and A prime. And then the last one has both A and B primed. Now, that's the minterm expansion that we found for F. And again, we are now asked to find the max term expansion. Well, there's a very easy way to do it. The first step, okay, let me emphasize, this is algebraic notation, where we've spelled out all the variables. But it's very handy here to use decimal notation, and so we'll go as follows. Remember that for minterms, when we want to label them using the decimal notation, we look for when they are equal to 1. So we have 1, 1, 1, 1, 1, 1, 1, 0, 1, 1, 0, 1, 1, 1, 0, 0, 0, 1, 1, 1, 0, 0, 1, 1. And if we interpret each of those as a binary number, then this is 15. Let's see, this will be 8 and 4 and 2. So that will be 14. 1, 8 and 4 and 1 is 13. 8 and 4 is 12. 4 and 2 and 1 is 7. And 2 and 1 is 3. So if we write the minterm expansion for F in decimal notation, now this is a minterm expansion, so it's a sum, and that's why we use this symbol, and minterms get a lowercase m, and so we will have 3, 7, 12, 13, and 14. And this is minterm expansion for F. In decimal notation. Now, how do we find the max term expansion in an easy fashion? Well, we can simply write it down. F of A, B, C, D will be equal to M0, capital M, 0, 1, 2, 4, 5, 6, 8, 9, 10. Recall, I'm sorry, I left out the 15 up here. You see that the first term was 15, and I simply left that out, so 15. Now continuing down here with the max term expansion, we have 0, 1, 2, 4, 5, 6, 8, 9, 10, 11, and that is it. That is the max term expansion in decimal notation. And if you compare with what we had before, you can see indeed 0, 1, 2, 4, 5, 6, 8, 9, 10, 11. Now, do you see how I got that answer? Well, the answer is the following. How did I get it? I simply looked at the minterm expansion and I thought about what this means. Remember that if you try to visualize the truth table for F, this information tells you that in the 0011 row and the 0111 row, and in the 1100 row and the 1101 row and the 1110 row and 1111 row, in other words, in rows that correspond to the numbers 3, 7, 12, 13, and 14, and 15, F is equal to 1. And therefore, in all the other rows, F is equal to 0. But that's exactly how we name the max term expansion, is by looking at the rows where F is equal to 0. And those rows will be the rows corresponding to the numbers 0, 1, 2. We don't have 3 because 3 is up here. Then 4, 5, 6, but we leave out 7 because 7 is up here. 8, 9, 10, 11, but then we don't have 12, 13, 14, or 15 because they're up here in the minterm expansion. And so that's it. It's just that easy. And therefore, to do a problem like this very efficiently, notice that this problem took us quite a bit of time, but actually would have been quite simple, because we started out with this SOP expression. We got the minterm expansion very easily, and then from the minterm expansion, we can get the max term expansion very easily as well. So that's how we would do a problem like that. Now, in the B part of that problem, you're actually given, let's see here, if I wrote the right problem number. I wrote the incorrect problem number here. I said that this was problem 430, but this problem that I've just done is 429. And if you look at 429b, you start out with a product of sums expression rather than a sum of products expression. And so in that case, it may be easier, rather than multiplying everything out, it may be easier to go ahead and find the max term expression first. Since it's already a POS expression, it might be easier to find the max term expression first, and then using this same technique, you would write the max term expression in decimal notation, see which terms are not there, and you could immediately get the minterm expansion. So keep in mind that technique, because it can really save a lot of time. Now, the well, let's stop there for just one moment. Yes, I see, actually, we've taken up enough time for one period, so I'll go ahead now, rather than covering any more material in this lecture, I'll actually make up a couple of questions. So let's look now at the problems for this lecture. 9.1 says, suppose f of a, b, c, or d is equal to the sum of the minterms 0, 1, 2, 6, 7, 13, and 15. And by the way, as I said, this is called decimal notation. I believe we mentioned in our previous lecture it's also called little m notation. But the question here is the following: if that's the expression for capital F, which of these is the minterm expansion for F prime? Now, be very careful to notice this is F prime. It's not F itself, it's the complement of F. So we want and F prime, of course, is also a function of the variables A, B, C, and D, just like F is, but we want the minterm expansion for F prime. And here are your expressions, your possible answers, A, B, C, and D. And then for 9.2, we're given a formula, F of the variables A, B, C, lowercase variables A, B, C, is equal to A ANDed with the sum of B ORed with C prime. So this is our formula for little f, and we are asked to find the max term expansion for f of ABC, this same function, in capital M notation. Now each one of these you see has the capital M notation, so you don't have to worry about that. There's no tricks here, but you just need to find out which of these capital M notation expressions, which of these expressions is the correct minterm expansion for this function. So that concludes Lecture 9, and good luck.